Assalamu alaikum dear students. I hope you're all fine by the grace of Almighty Allah. I welcome you all to the 21st lecture of Thermodynamics 2. Lecture 21. The contents of lecture 21 are exergy of a finite body, quality of energy, exergy of a closed system, numerical problems, and conceptual questions and answers. Exergy of a finite body, that is a temperature of T1. So a body is shown at at a right hand side a body is shown, so that is a temperature of T. As heat is transferred, the temperature of body will fall. So as we have discussed two different types of bodies, one is that is a finite body, and what is one a body that represent a reservoir. So you must remember the difference between the finite body and a reservoir body. So a reservoir is a body that has a constant temperature with an infinite specific heat value. So when a heat is rejected from a reservoir, the temperature of a body of a reservoir will remain constant. For example, a reservoir that is a temperature of 100 degrees centigrade will have a fixed temperature of 100 degrees centigrade. How much amount of heat is added to the reservoir or taken out of the reservoir is uh, doesn't affect the temperature of the reservoir. So if you take amount of heat out of a reservoir or absorb energy into the reservoir or reject heat into the reservoir, the temperature of the reservoir is constant. And in contrast of a reservoir, we have a finite body. So a finite body has a limited heat content and has a specific value of heat capacity. So whenever a heat is added to the body, that is a finite body, then the temperature of a body will increase. And if heat is rejected or taken out of a finite body, then the temperature will be reduced. So here we have a body that is a finite body and that is a temperature of T. And whenever a heat is transferred or rejected from that body, the temperature of the body will fall. So in the previous lecture, we have a heat engine that was connected to a thermal energy reservoir. So now that same heat engine, so in the previous lecture we have calculated different form of uh, equation and relation to calculate the value for the loss of available energy, decrease in available energy, or increase in unavailable energy. So in the previous lecture we have found or calculate or derived five different relation to find out these values. And now in the current lecture, that reservoir is replaced with a body. So now in this lecture we will find what is the difference between the relation when a body is connected to a heat engine, a finite body, or a thermal energy reservoir body. So in the current lecture we have a body that is a temperature of T naught T and surrounding that is a temperature of T naught. So the surrounding uh, is an ambient or dead state. So a dead state is represented with the help of T naught temperature. So here to calculate the value of exergy or available energy, we have connected the heat engine with a body. So heat engine is connected to finite temperature body, that is the temperature of T. So the work produced by the heat engine is the useful work, and that useful work represents the exergy or available energy. So the thermal energy from body will flow into the heat engine. Useful work, that is the exergy or available energy, will be taken out on the right hand side, that is W useful, and Q naught amount of energy is the amount of unavailable energy that will be rejected into the atmosphere. So now according to the first law of thermodynamics, the heat supplied to the heat engine is the Q amount of heat is supplied to the heat engine. W amount of heat, W amount of work is converted by heat engine. So W useful is W amount of work is produced by the heat engine, and Q naught amount of heat is ejected by the heat engine into the surrounding. Q naught is the unavailable energy. So if we take Q naught on the left hand side, and then Q naught is equal to Q minus W. So Q naught represent the amount of unavailable energy. So unavailable energy is equal to Q minus available energy, because W represent the available energy term. Now the available energy in the above expression, so that is the above expression. So here available energy represent the value of exergy that we want to calculate. So now from the relation of entropy for isolated system, so that is the schematic diagram that was in the previous slide. A heat engine that is connected with a finite body that is at temperature of T. Heat engine absorb Q amount of heat from source and reject Q naught amount of heat into surrounding, and W useful amount of work is produced by heat engine. That W useful was exergy or available energy, and that Q naught is the amount of unavailable energy. So now we have a mathematical relation over here. So for an isolated system, we have a generalized expression for change of entropy for universe is equal to 0. So universe represent universe composed of system and surrounding. So change of entropy of system plus change of entropy of the surrounding. So if that is a reversible process, so here because we have used the equal sign, so this is a reversible process as well. So change of entropy of surrounding will be equal to 0, and change of system, so system consists of a finite body and a reservoir. So the body is at temperature T is a finite body, and the reservoir that is a temperature of T naught is a reservoir. So change of the entropy change for both of these, the finite body and the reservoir, represent the change of entropy of the system. Now here we have a relation for the change of entropy of finite body. So here is a body that is initially at a temperature of T. So as I have already told you, that is a characteristic of a body. When a heat is rejected from a body, then the temperature of a body will reduce. And when so this is a finite body, so when heat is rejected from the body, the temperature of finite body will reduce, and when heat is added to the finite body, the temperature of finite body will increase. Now when a heat engine is connected to that body, so heat will transfer from that finite body into the heat engine, and after some time temperature of the finite body will start reducing, and heat will engine will continue to produce work. And let's suppose the initial temperature of is 100 degrees centigrade and temperature of surrounding is 25 degrees centigrade. So as the heat will continue to move, this temperature of a body will continue to decrease, so that 100 will decrease to 90, 80, 70, 60, 50 and 40, 30, and then at last the temperature of the body will become equal to the surrounding, that is a 25. And as the temperature of body reaches the temperature of surrounding, and both the temperature of body and the surrounding is equal, then heat engine will stop to produce work. So heat engine, because the temperature difference is zero, then heat engine will stop to produce work. So now the as the temperature of body, the initial temperature was T and the final temperature was T naught. So we have already derived that relation in the chapter of entropy. So the change of entropy is mCp natural log T naught over T. T naught is the final temperature and T is the initial temperature of the finite body. And since the here T naught is the temperature of reservoir, so to calculate the entropy change for the reservoir, we have Q naught over T naught, or the heat that is entered into the reservoir divided by the temperature of reservoir. So all that is equal to 0. So in the next step, that Q naught is equal to the difference of heat that is entering into the heat engine and work that is produced by the heat engine. So Q is the amount of heat that is absorbed by heat engine, and W is the amount of work, useful work, that is produced by the heat engine. So Q naught is replaced by Q minus W. So in the last step, we have multiplied both sides with the T naught temperature. So T naught is the temperature of thermal energy reservoir, that is the sink for acting as a sink for that heat engine. So that heat engine is rejecting the heat into the ambient. So you must remember, whenever Q naught or T naught is mentioned, so we have already studied about the dead state. So the temperature T naught and the energy that is rejecting into the dead state represented by Q naught. So T naught and Q naught is to denote the dead state. So that is the last step on the previous slide. We have multiplied both sides with the T naught term. Now if we take the W term on the one hand left hand side and all other term on the right hand side, then it is equal to W is equal to Q plus T naught mCp natural log T naught over T. So as we are talking about exergy, so in the textbook, to represent the exergy, so you know that exergy is the available energy. So in the textbook, the symbol X is used to represent the exergy term. So whenever you see X is written, so it means exergy, or available energy, or availability, or useful work. So all the term means the same. So exergy is represented with the symbol capital X. So capital X or exergy is equal to Q. So the Q is the amount of heat that is absorbed by heat engine, plus T naught is the temperature of sink, M is the mass, Cp is the specific heat, natural log T naught over T, T naught and T are the temperature of reservoir and body respectively. So now Q, if we are talking about Q, so Q is the heat transfer. So Q may be replaced by mCp delta T. So as you know the relation of Q, that is mCp delta T. So as the Q is the amount of heat that is leaving the body, so delta T will be the initial and final temperature. So the heat is replaced by mCp delta T. T is the initial temperature, T naught is the final temperature. So exergy is equal to mCp T minus T naught plus T naught mCp natural T naught over T. So now here if you see that mCp is the common term in both, is the common term in both uh, left right hand side terms. So MCP will be taken as a common, and in the bracket we have t minus t naught from the first relation and t naught natural log t over t naught over t from the second relation. So in the mathematics we know that to convert natural log into simple log we have 2.303 term that we multiplied to convert the natural log into uh, base 10 log. So here Exergy is equal to MCP t minus t naught plus t naught into 2.303 log base 10 into t naught over t. So this is the next topic, that is the quality of energy. So in the previous lecture we have studied a topic, the qualitative law and quantitative law. So the first law of thermodynamics is known as quantitative law, and the second law of thermodynamics is also known as qualitative law. So in the previous lecture we have studied what is meant by quality, what is meant by the quality of energy, and with the help of a heat engine that is connected with two different temperature thermal energy reservoir or source. So a heat engine that is connected with 1000 degrees centigrade reservoir and 800 degrees reservoir, but the amount of heat Q is same, that is absorbed by the heat engine from both reservoir. So first law suggests that there is no difference because the quantity of heat that is supplied by the reservoir to the heat engine is same, whereas second law of thermodynamics suggests that there is a significance of temperature or reservoir that is at a certain temperature. So the heat supplied by a reservoir that is at a higher temperature will have more significance than the heat supplied by a heat engine, the heat supplied by a source that is at low temperature to the heat engine. So the source that supply heat at a higher temperature to the heat engine will have more significance. So that include the qualitative analysis, and that is why second law is also known as qualitative law. So now that to conclude the discussion, I have the topic that was discussed in the previous lecture. I have repeated that because that slide or that topic, quality of energy, is linked to somewhat to that topic as well. So energy is an important tool to quantify the quality of the energy. So exergy, exergy provide the tool or the method to quantify the quality of energy. So exergy is the available energy. So if we have a certain amount of energy, so we have two source, they both contain 100 kilojoule of energy. Source 1 also contain 100 kilojoule of energy, source 2 also contain 100 kilojoule of energy, but the exergy or available energy or availability that is provided by the source 1 is greater than source 2. For example, the available energy that is provided by source 1 is 50 kilojoule. So I will write it down. So for example, if we have two, so here we have S2 and here we have S1. So both have 100 kilojoule of both have 100 kilojoule of total energy content. But when we talk about exergy or available energy, then it provides 50 and it provides 30 kilojoule of usable energy. Then exergy is an important tool to relate how much importance of source is there, which source is more important and which source is more significant, and which source has a higher quality of energy stored within it. So both sources have 100 kilojoule of energy, but if we convert that energy into exergy or available energy, then we came to know that one source provide a higher exergy or available energy and other provide a lower value of available energy. Therefore, exergy is an important tool to quantify the quality of energy. So quality of energy can be known with the help of exergy value. So for example, if we have two pipelines that are carrying fluid within it, and within a pipeline 1 we have a fluid that is at a temperature of 800 Kelvin, and in pipeline 2 we have a fluid that is at 300 Kelvin temperature. So 300 means, if we are talking in the centigrade, so 300 is approximately 27 degree centigrade. So if we have a fluid that is at 27 degree centigrade, and if we have a fluid that is greater than 500 degree centigrade, so now we know that these pipe that are carrying it will have a certain temperature difference from the surrounding. So let's suppose that in the surrounding we have a certain temperature 5 or 10 degrees centigrade. So the main thing is the same amount of heat is rejected by both pipe. So let's suppose the value of Q is 10 kilojoules. So 10 kilojoule of energy is rejected by the pipe 1 that is a temperature of 800 Kelvin, and the same amount 10 kilojoule of energy is rejected by the pipe that is at a temperature of 300 Kelvin to the surrounding. So now the quality of energy suggests that is based on the second law of thermodynamics. So what that suggests is that the heat that is rejected by 800 Kelvin temperature pipe is more precious. So here the word is precious is used. So heat rejected by 800 Kelvin pipe is more precious because it contains greater value of quality than 300 Kelvin temperature. So now it is a duty or responsibility to provide it with a certain amount of become to if there will be a resistance, so to become the idea the process will become adiabatic, and we will stop that amount of heat that is rejecting out of 800 kilo Kelvin pipe. So here it is written that reason is precious. So what is the reason? So precious Q rejecting is carrying greater portion of available energy and lesser portion of unavailable energy. So as you know that the total heat and total energy is the sum of available and unavailable energy. So as the available energy increases, the unavailable energy decreases. So must you I have already studied that. So the next topic is exergy of a closed system. So on the right hand side, a closed system is shown, and closed is a piston cylinder system is shown, and a gas is present between the piston and enclosed in the cylinder, and the piston is on the top, and the certain atmospheric pressure is also acting on the piston. So the blue arrow represent the atmospheric pressure on the piston, and Q amount of heat is added into the system, and in the result of this added heat the gas will expand, and we have a work. So the work will be on the piston, and piston will move in the upward direction. So in the state 1, the piston is at state 1 when no heat is added to the system, and as the heat is added to the system, so piston will rise and move to state 2. So here the blue arrow represent the work. So the maximum work is the sum of useful work plus surrounding work, and useful work is equal to maximum minus surrounding. So W max, as you can see that the maximum work is in the upward direction, whereas surrounding work is in the downward direction. So as they both have opposite direction, therefore there is a negative sign as well, and W useful is equal to W max minus, so the surrounding work, as this is a closed system, so work can be replaced by integration P dV. So here the change in volume, so volume will increase from state 1 to state 2, so there will be an increase in the volume. So final volume is V2 and the initial volume is V1, so there is an increase in the volume. So the increase in the volume multiplied the pressure, that is an atmospheric pressure, is equal to work done by the surrounding. So now according to the first law of thermodynamics, Q is equal to del U plus W, and also according to second law of thermodynamics, we have the change of entropy relation, that is del S is equal to Q by T naught. And for the reversible process, we have Q is equal to T naught delta S. So if we replace the value of Q is equal to T naught del S in the relation for the first law of thermodynamics that we have in the above, so here Q is replaced by T naught del S. So T naught del S because the entropy is a state property, so it can be written as S2 minus S1, and internal energy is also a state property, so it is written as U2 minus U1, and W is the maximum amount of work. So if we take the W max term on the left hand side, so we are left with the U1 minus U2 plus T naught S2 minus S1 term on the right hand side. So in the last slide, we have calculated the relation for maximum work, that is U1 minus U2 plus T naught S2 minus S1, and the relation for W useful was calculated with the help of first law of thermodynamics. So here we have calculated the W useful relation for this closed system. So when we plug the value of W max into the relation of W useful, then we have the relation that is W useful is equal to U1 minus U2 plus T naught S2 minus S1 minus P naught V2 minus V1. So P naught V2 minus V1 is the work done for the closed system relation, and V2 and V1 is the change in the volume when Q amount of heat is added to the system. So piston will rise from, and the position of the system will change from state 1 to state 2. So there will be an increase in the volume. Piston will move up, and P naught is the amount of pressure that is acted on the piston from upside down. So the P naught pressure is pushing the piston down and the heat energy is pushing the piston up. So P naught is the atmospheric pressure. So here we have a simple simplification, and W useful is equal to U1 minus T naught S1 plus P naught V1 minus U2 minus T naught S2 plus P naught V2. So here we have just taken one this term that have a subscript 1 for the state 1 property on one side and state 2 property on the other bracket. So in the one bracket we have already, you can see we have all term with the subscript 1, and in this next bracket we have all term with the subscript 2. So now we will introduce a function that is represented with a symbol phi, that is known as the availability function. So the availability function that is represented with the symbol phi is equal to u minus t naught s plus p naught v. So the sum of all these terms is equal to the availability function. So W useful is the availability function for state 1 minus availability function for state 2. So here availability function, so change in the available energy, W useful is the change in the available energy. So change in the available energy is represented in term of availability function. So phi 1 and phi 2 are the availability function for state 1 and 2. So change in the available energy is represented in terms of availability function. So the assumption for the availability function are change in the kinetic and potential energy is negligible. So you will only use that relation when the change in the kinetic and potential energy are negligible. So we will discuss in detail when we'll be solving the numerical problem as well, how we'll use these relation to solve our problem. So conceptual question answer. In an actual control volume process is reversible, what can you say about the work done? So you are asked about the reversible work. So as you know that the reversible work is the maximum amount of work that can be produced with the process. So if the process is a work producing, so if the reversible work is the reversible process a work producing process, then the work produced is the maximum amount of work. And if the device is work consuming device, then the work supplied will be minimum. So for the reversible process, if the device is work producing, then work obtained will be maximum, and if the device is work consuming, then the work supplied will be minimum. Can entropy change in a control process that is reversible? So you are asked If the process is reversible, will the value of entropy will remain constant or it can change? So the short answer is that the entropy can change for the reversible process as well. So a flow in or out at a state with a different entropy than the average entropy inside, or a heat transfer will change the entropy. So a certain amount of heat added or leaving the system, or the entropy, the heat transfer within the process will also change the entropy of the system as well. So all the terms that change the entropy are transfer terms, so there is no net increase generation of entropy. So as you know that the entropy mechanism or transfer of entropy mechanism consists of mass transfer and heat transfer. So the overall entropy for the reversible, because due to reversible process there will be no entropy generation, so the entropy will overall entropy of the system will remain constant, but however within the system the entropy can change. So energy can be stored as internal energy, potential energy, or kinetic energy. Are those energies are 100% available? So the answer is the internal energy is only partly available. A process like expansion give out work, or if it cools by heat transfer out, only partly available as work. So you are asked that there are three basic type of energies: internal energy, potential, and kinetic energy. Which of that will is 100% available? So internal energy is not 100% available, rather it is partly available. And for potential and kinetic energy, these are 100% available. But as the kinetic energy is depend upon the motion, so there may be a certain loss of kinetic energy due to the mechanical work, or the frictional loss due to the motion of mechanical equipment. We cannot create nor destroy energy. Can we create, destroy exergy? So that is another conceptual question answer. So the answer is yes, every process that is irreversible to some degree destroy exergy. This destruction is directly proportional to the entropy generation. We cannot create exergy, it remain constant in the case of reversible process. So the question asked was, can exergy or available energy be destroyed? So as you know that available energy is limited to the irreversibility of the process. If the process is more and more irreversible, then the available energy will reduce and reduce further. So irreversibility will generate a term that you know that the entropy generation term is introduced due to the irreversibility of the process. So as the entropy generation is increased due to the more irreversibility of the process, so as more the process is irreversible, the entropy generation term will be greater and exergy term will decrease. So in only in the reversible process the exergy will remain constant, but in the irreversible process, as more the irreversible process is, the exergy is decreased. So the numerical problem is, during a thermodynamic process 100 kilojoule of heat is transferred from a reservoir at 800 Kelvin to a sink that is at 400 Kelvin. The ambient temperature is 300 Kelvin. Calculate the loss of energy. So here a heat engine is connected to a source and a sink. So initially a source that is at temperature, a thermal reservoir that is at temperature of 800 Kelvin is connected to another thermal reservoir that is at a 400 Kelvin temperature, and then that thermal reservoir is connected to heat engine, and that heat engine is connected to sink that is a temperature of 300 Kelvin. Heat engine will produce a certain amount of useful work. So now the question is to calculate the loss in the energy. So initially the heat engine was first connected to 800 Kelvin reservoir, and then in the case 2 the heat engine is connected to 400 Kelvin temperature reservoir. So we want to calculate what is the loss of exergy when the heat engine is connected to 800, and then what is the value of available energy when it is connected to 400. So the difference of available energy when the heat engine is connected to 800 400 Kelvin reservoir will represent the loss in the energy. So here loss in the available energy is the available energy 1 minus available energy 2. So available energy 1 is the one that when the heat engine is connected to 800 Kelvin temperature reservoir, and available energy 2 is the energy that when the heat engine is connected to 400 Kelvin temperature reservoir. So here we have already uh, know this relation, we have derived this relation, so we have to only plug in the values. So T1 is the temperature of reservoir that is 800, and T2 is the temperature of reservoir that is 400 Kelvin. So loss in the available energy is 37.5 kilojoule. So that is the same numerical, but that is a different methodology. Here we have utilized the value or relation for the change of entropy. So now we know that the entropy change for the reservoir is Q by T. So T1 is the temperature 800 and T2 is the temperature 400. So when we plug in the value, we have the same answer as in the previous slide as well. So calculate the available and unavailable energy in 40 kg of water at 75 degrees centigrade with respect to surrounding that is at 5 degrees centigrade. Pressure of water is 1 atm. So here we have a certain mass of water that is some certain temperature, and here we have a surrounding that is at certain temperature. So heat is exiting out of the water. So here we have to calculate the available and unavailable energy. So Q is equal to mCp delta T. That is the relation we have already known. So the difference of temperature is 75 minus 5 degrees centigrade. So as that is a difference, so we don't need to convert that into the Kelvin scale as well, because the difference of Kelvin and centigrade is same. So we don't need to convert that into the Kelvin scale. So the value of Q is 11760 kilojoules, and here we are calculating the exergy value. This relation we have already derived that. So mCp T minus T naught, T naught natural log T naught over T. So here T is the temperature of water and T naught is the temperature of the surrounding. When we plug in the values, so the value of exergy is 1340 kilojoule. So Q is the total amount of energy that is present within the water. Exergy is the available amount of energy. The difference of total energy minus available energy is equal to unavailable energy. So the difference of total minus available is unavailable energy. So when we subtract the both, we find the value of unavailable energy, that is 10420 kilojoule of unavailable energy. So the next numerical is for steady state process from state 1 to 2, enthalpy changes from H1 to H2. H1 value is 400 kJ per kg and H2 is 100 kJ per kg. And entropy changes from S1 to S2. S1 is 101 kJ per kg Kelvin and S2 is 0.7 kJ per kg Kelvin. The surrounding temperature is 300 Kelvin. For negligible change in kinetic and potential energy, find the change in availability of the system. So that is a question. We want to find the availability of the system. So here the change of availability is equal to exergy of the system. So we know the relation. So delta H is equal to T naught delta S. So we know all the values of H1, H2, S1, S2 and T naught is the temperature of the surrounding. We plug in all the values. So state 1 enthalpy, state 2 enthalpy, surrounding temperature, state 1 entropy and state 2 entropy. So the value of exergy is 180 kilojoule per kg. So that is the last numerical for the lecture. Air expand through a turbine from 500 kilopascal 520 degrees centigrade temperature to 100 kilopascal and 300 degrees centigrade temperature. During the expansion, 10 kilojoule per kg of heat is lost to the surrounding, which is at 98 kilopascal and 20 degrees centigrade temperature. Neglecting the change in kinetic and potential energy, determine the following. So here we have to calculate the decrease in availability, the maximum work and the irreversibility. So here you can see the turbine schematic diagram is shown. The inlet properties are on the left hand side, the outlet properties are on the right hand side. The Q amount of energy that is lost into the environment is shown by the arrow. The properties of the environment or dead state are also mentioned here. So decrease in availability, change in availability or loss in the available energy or work done by the turbine in this case, all these four things mean the same. So in the question here it is asked to you that to calculate the decrease in availability. So it may be mentioned here as you want to calculate the change in availability, loss in available energy or work done by turbine. So for all four of these relation you will do the following calculation. So here we have utilized the relation. So that is the relation of H1 minus T naught S1 minus H2 minus T naught S2. So here we have different temperature and pressure values as well. So the work done by the turbine is calculated by H1 minus H2 minus T naught S1 minus S2. So as the working fluid is air, so we can use we can replace the H term with the CPT. So enthalpy is the function of temperature. So for the ideal gas, we are using it as CPT. So temperature and entropy values are given. So further the this relation for the change of entropy for air we have calculated in the lecture 17 as well. So we already know how to calculate the change of entropy value. So as you can remember, we have calculated three different form of change of entropy value for ideal gas, and as air is the ideal gas, so we can use either of that value. So I've already told you that one relation was between temperature and pressure, the other was between temperature and volume, and the third one was between pressure and volume. So I've told you we will use the relation according to the data provided to us in the numerical. So in the current numerical we have been given the value of temperature and pressure, so we'll use the this change of entropy for ideal gas relation. So we know the values, so we know the T1, T2, T naught, Cp natural log R value for air. So the work done in turbine is 260.7 kilojoule per kg. Now for irreversibility, so here we have represented irreversibility with the capital I, that is equal to T naught del S universe. So del S universe composed of system and surrounding. So for neglecting system, so system entropy is S2 minus S1, and surrounding is a thermal energy reservoir because it is an ambient and dead state. So Q amount of heat that is leaving the system or rejected by the turbine, so the heat content of the system will decrease and the surrounding heat content will increase. So due to the transfer of heat there will be always a entropy transfer. So entropy is transferred to the reservoir. So entropy for the reservoir is equal to Q by T naught. So similarly here we have used the ideal gas equation for the entropy change calculation. So we know all these values. When we plug in these values for Cp, T2, T1, R, P2, P1, Q, T naught, so the irreversibility value is 49.6 kilojoule per kg. So that summarizes our numerical problem. So home assignment for lecture number 21. All students are advised to go through example problem of each topic discussed in this lecture. So the topic discussed in this lecture, you must go to your textbook and go through example problem for each topic, and you are also advised to consult the exercise question as well. You are advised to write a handwritten lecture summary report, scan it, take a picture and send it to my email ID, and you are advised to prepare this lecture thoroughly as there will be a question answer session when there will be online video session. Thank you very much. Allah Hafiz.